I am Dr.Bindhu, Assistant Professor, Department of Science and Humanity, Emmanuel Arasar JJ College of Engineering, Nattalam. I will explain the elementary matrices. Then row elementary matrix. An n by n matrix is called an elementary matrix if it can be obtained from the identity matrix I by a single elementary row operation. Then elementary matrix means n by n matrix. Then n by n means number of rows and number of columns are equal. Then take the identity matrix I. Then by a single elementary row operation is applied that this matrix is called the elementary matrix. The definition: the elementary reduction matrices are obtained from identity matrices with one Gaussian operation. We denote them. Then first one, then identity matrix 2, then k into row I, then mi of k for k not equal to 0. Second condition is identity matrix 2, row I2, row j, then pi comma j for I not equal to j. Then third condition is identity matrix 2, k into row I plus row j, ci comma j of k for I not equal to j. This is a elementary reduction matrices. Then not only do a single elementary row operations. Then this elementary matrix means only one single elementary row operation. Then example, elementary matrices and non-elementary matrices. First one, 1 0 0 C 3 0 0 0 1. This matrice's order is 3 by 3. Number of rows and columns are equal. Then only one row operation is applied, 3 into row 2 of I3. So this matrix is a elementary matrix. Then second one, 1 0 0 0 1 0. This matrix is non-elementary matrix. That means this matrix number of rows 2, number of columns 3. Then number of rows and columns are not equal. So this matrix is non-elementary matrices. Then third one, 1 0 0 0 1 0 0 0 0. This matrix is non-elementary matrix. That means row multiplication must be by a non-zero constant. Then fourth one, then matrix is 1 0 0 0 0 1 0 1 0. This matrix is elementary matrix. That means then row 2 to row 3 into I3. This single row operation is applied to this matrix. So this matrix is a elementary matrix. Then fourth one, 1 0 2 1. This is a square matrix. Number of rows 2, number of columns 2. Then one condition is true. Then the single row operation, single elementary row operation is applied. Then condition 2 row 1 plus row 2 into I2. So this matrix is a elementary matrix. Then last one, 1 0 0 0 2 0 0 0 minus 1. This matrix is a square matrix but not elementary matrix. Then that means use two elementary row operation is applied. Then elementary matrix, then only single row operation is used. That this matrix two row operations are applied. So this matrix is not a elementary matrix. Theorem representing elementary row operations. Let E be the elementary matrix obtained by performing an elementary row operation on IM. Then if that same elementary row operation is performed on an m by n matrix A, then the resulting matrix is given by the product E into A. Then first take elementary matrix E, then other elementary row operation on IM. IM is a identity matrix, then order is m by m. Then next, then matrix m by n order matrix is A. Then the product matrix is EA. Then row of I equal to E, then row of A equal to EA. No. Then first one, row ij of A equal to Pij into A, K into row I of A equal to Mi of K into A. Third one is K row I plus row j into A equal to Cij of K into A. Then example, using elementary matrices. Find a sequence of elementary matrices that can be used to write the matrix A in row echelon form. Then A matrix is given there. Then solution, first we can write the E1, E2, E3 values. Then E1 equal to, then formula row 1, 2 into I3. I3 is a identity matrix in 3 by 3 order. Then the E1 value is 0, 1, 0, 1, 0, 0, 0, 0, 1. Then next we can write E2 matrix, then formula minus 2 row 1 plus row 3 into I3. Then I3 is a identity matrix in 3 by 3. Then multiplying the value minus 2 row 1 plus row 3. Then answer is 1, 0, 0, 0, 1, 0, minus 2, 0, 1. Then next E3 value, E3 1 by 2 row 3 into I3. Then identity matrix is multiplying the value of 1 by 2 into row 3. Then 1, 0, 0, 0, 1, 0, 0, 0, 1 by 2. Then next find the value of A1, A2, A3. Then A1 is row 1, 2 of A equal to, then row 1, 2 is E1 into A. Then first write the E1 value 0, 1, 0, 1, 0, 0, 0, 0, 1. Then next write the A matrix value. Then A matrix value is given the problem. Then A matrix is 0, 1, 3, 5, 1, minus 3, 0, 2, 2, minus 6, 2, 0. Then multiplying the two matrices, then answer is 1, minus 3, 0, 2, 0, 1, 3, 5, 2, minus 6, 2, 0. The next find the value of A2. Then A2 equal to minus 2 row 1 plus row 3 into A1. That is equal to minus 2 row 1 plus row 3 value is E2 into A1. Then write the E2 and A1 value. Then E2 value is 1, 0, 0, 0, 1, 0, minus 2, 0, 1. A1 value is find the previous line. Then matrix is 1, minus 3, 0, 2, 0, 1, 3, 5, 2, minus 6, 2, 0. Then multiplying the two matrices, then the final answer is 1, minus 3, 0, 2, 0, 1, 3, 5, 0, 0, 2, minus 4. Then we can find the next value is A3. Then A3 equal to 1 by 2 row 3 into A2 equal to 1 by 2 into row 3 value is E3 into A2. Then write the E3 and A2 matrices. Then multiplying the two matrices, then final answer is 1 minus 3 0 2 0 1 3 5 0 0 1 minus 2. This is equal to B. This form is a row echelon form. So then A matrix is a sequence of elementary matrices that is B equal to E3 into E2 into E1 into A. Or then we can write B equal to, then E3 value is 1 by 2 into row 3, E2 value is minus 2 row 1 plus row 3, then E1 value is row 1 2 into A. This is a sequence of elementary matrices. Row equivalent. Matrix B is row equivalent to A if there exists a finite number of elementary matrices such that capital B equal to Ek minus 1, then etc. E2, E1, A. Then is a row equivalent matrix. Then finite number of elementary matrices E1, E2, etc. Ek. Then the condition B equal to Ek into Ek minus 1 into etc. E2 into E1 into A. Theorem: elementary matrices are invertible. If E is an elementary matrices, then E inverse exists and is an elementary matrix. Sum on elementary matrix E, then we can prove that E inverse exists and it is an elementary matrix. Note: Pij the whole inverse equal to Pij. Mi of k the whole inverse equal to, then answer is mi of 1 by k. Cij of k the whole inverse, the answer is Cij of minus k. Example: elementary matrix and inverse matrix. Then write the elementary matrix E1 of R12 equal to 0 1 0 1 0 0 0 0 1, that is equal to P12. Then write the inverse matrix P12 of the whole inverse. Then first note value is, see the first note, Pij the whole inverse equal to Pij. Then Pij value is P12. Then next P12 the whole inverse. These two P12 and P12 the whole inverse are equal value. Then P12 the whole inverse equal to E1 inverse equal to the same value P12 0 1 0 1 0 0 0 0 1, that is equal to P12. The next write the value of E2 of minus 2 row 1 plus row 3 equal to, then elementary matrix 1 0 0 0 1 0 minus 2 0 1. This value is C13 of minus 2. This then we can see the second note MIK, third note Cij of k the whole inverse equal to Cij of minus k. Then ij value is 1 3, k value is 2. Then then inverse matrix value is C13 2 minus 2 C13 minus 2 of the whole inverse equal to the same value 1 0 0 0 1 2, then multiplying the minus in this matrix 1 0 0 0 1 0 2 0 0, multiplying the minus in row 3, then answer 201, that the value is C13 of 2. Then next last E3 value, E3 of 1 by 2 into row 3 equal to 1 0 0 0 1 0 0 0 1 by 2. This value is M3 of 1 by 2. That is equal to next M3 of the, write the inverse matrix M3 of 1 by 2 the whole inverse. We can see the second note, Mi of 1 by k equal to Mi of k inverse. Then the same value of 1 0 0 0 1 0 0 0 2, that is equal to M3 of 2. Next theorem, a property of invertible matrices. A square matrix A is invertible if and only if it can be written as the product of elementary matrices. Then square matrix is invertible, then other part is then the product of elementary matrices. Then first one, as then the proof is, then if and only if condition, first assume that the second part, assume that A is the product of elementary matrices. Then element already I can explain the elementary matrix is invertible. Then so first every elementary matrix is invertible, then product of invertible matrices is always invertible, so A is invertible. Then second part, converse part, then conversely assume that A is invertible, then to prove that then the product of elementary matrices, then A is invertible, then Ax equal to 0 has only the trivial solution. Then A matrix of AM to IM, then A is a, and then given invertible matrix, then M is other matrix equal to identity into M, then implies the sequence of elementary matrices Ek etc. E3, E2, E1 into A equal to identity matrix. Then we can write the A equal to, then all the elementary matrices take the right hand side, then the inverse, then write the inverse matrices E1 inverse, E2 inverse, E3 inverse, then etc. Ek inverse. So A can be written as the product of elementary matrices. Example, find a sequence of elementary matrices whose product is A equal to minus 1, minus 2, 3, 8. Then solution, then A equal to minus 1, minus 2, 3, 8. Then this matrix is converted to, then apply to the multiplying the minus in row 1, then 1 2 3 8. Next we can use the condition minus 3 row 1 plus row 2 in previous matrix, then the answer, then first row the same value 1 2, then second row, then apply to the condition minus 3 into row 1 plus row 2, then the answer is 0 2. then next matrix, then apply to the condition 1 by 2 row 2 in second row, then first row the same value 1 by 2, then second row divided by the 2, then answer is 0 1. Then next matrix, then we can apply to the condition minus 2 row 2 plus row 1, then the answer is first row value is 1 0, then second row value is same value 0 1. This matrix is a identity matrix I. Therefore C21 minus 2 into M2 of 1 by 2, C12 of minus 3, M1 of minus 1 into A equal to I. This is a sequence of elementary matrices. Then A equal to M1 of minus 1 the whole inverse, C12 of minus 3 the whole inverse, M2 of 1 by 2 the whole inverse, C21 of minus 2 the whole inverse, that is equal to M1 of minus 1, then C12 of 3, then M2 of 2, C21 of 2. Since these lines I will explain the already 3 conditions in note. This note, this values then apply to this elementary sequences. Then M1 of minus 1 value is minus 1 0 0 1, then C12 of 3 value is 1 0 0 1, then M2 of 2 value is 1 0 0 2, then C21 of 2 value is 1 2 0 1. This is a elementary sequences. Then note, if A is invertible, then the condition ek etc. E3 E2 E1 into A equal to I. Then the write the A inverse value is ek etc. E3 E2 E1, then ek etc. E3 E2 E1 into A into M equal to identity matrix into M inverse. Theorem, equivalent conditions. If A is an n by n matrix, then the following statements are equivalent. Then n by n matrix is a square matrix. Then the 5 conditions are satisfied the matrix in n by n order. Then first one is A is invertible. Then second condition is Ax equal to B has a unique solution for every n by 1 column matrix B. Then third one is Ax equal to 0 has only the trivial solution. Then fourth one is A is row equivalent to In. In means identity matrix of n by n order. Next, then A can be written as the product of elementary matrices. These 5 conditions are equivalent conditions. Then the matrix n by n matrix of A. LU factorization. N by n matrix A can be written as the product of a lower triangular matrix L and an upper triangular matrix U, such as A equal to LU. L is a lower triangular matrix and U is a triangular matrix. Then A is a square matrix. Then the square matrix A can be written as a lower matrix into upper triangular matrix. Then note, if a square matrix A can be row reduced to an upper triangular matrix U using only the row operation of adding a multiple of one row to another another pivot element. Then it is easy to find an LU factorization of A. Then EK equal to EK etc. E2 E1 into A equal to U. Then A equal to E1 inverse, E2 inverse etc. EK inverse into U. Then A equal to L into U. This E1 inverse, E2 inverse etc. EK inverse value is a lower triangular matrix L. That is A equal to LU. Example, LU factorization. Then first one, A equal to 1 2 1 0. This matrix is a square matrix. Then this matrix, then second row, then apply to the condition -1 row 1 plus row 2. Then first row is same value, then next row values is applied to this conditions, then the value is 0 minus 2. This is a upper triangular matrix. Then second row, first column element is a 0, it is a upper triangular matrix. Then implies C12 of -1 into A equal to U. A equal to, then A equal to, then C12 minus 1 on the whole inverse into U equal to C12 of 1 into U equal to LU. That is L equal to C12 of -1 the whole inverse. That is equal to C12 of 1 equal to 1 0 1 1. This is a lower triangular matrix. Then say first row, second column element is a 0. It is a lower triangular matrix. Then next example, A equal to 3 by 3 matrix. It is a square matrix. Then first row, second row value is a same value, then write that. Then third row value is applied to the condition -2 row 1 plus row 3. Then the value is 0 minus 4 2. Then the next matrix, first row, second row is the same value. Then the third row is applied to the condition 4 row 2 plus row 3. Then the value is, third row value is 0 0 14. Then the upper triangular matrix U. Then upper value, then second row first column 0, third row first column second column element is 0. C is a upper triangular matrix, that is equal to U. Then implies C23 of 4 into C13 of -2 into A equal to U. Then implies A equal to, then this two values are, take the right hand side, C13 minus 2 the whole inverse, C23 of 4 the whole inverse into U equal to L into U. Then C13 minus 2 the whole inverse, C23 of 4 the whole inverse value is a L over triangular matrix into U. That is A equal to LU. Then L equal to C13 minus 2 the whole inverse, C23 of 4 the whole inverse equal to C13 of 2 into C23 of -4. Then C13 of 2 value is 1 0 0 0 1 0 2 0 1, and C23 of -4 value is 1 0 0 0 1 0 0 -4 1. These two matrices are same orders, then multiplying there, then the answer is 3 by 3 order matrix. Then answer is 1 0 0 0 1 0 2 -4 1. solving AX equal to B with an LU factorization of A. Then AX equal to B. If A equal to LU, then LU into X equal to B. Then A equal to LU is given there, then multiplying the X value, then AX equal to LUX, then AX value is B, that is LUX equal to B. Let Y equal to UX, then apply to the previous line, L into UX value is Y equal to B. Then two steps. First step is write Y equal to Ux and solve the equation Ly equal to B for Y. Then second step is solve Yx equal to Y for X. Example, solving linear system using LU factorizations. Then given the three linear equations, x1 minus 3 x2 equal to minus 5, x2 plus 3 x3 equal to minus 1, 2x1 minus 10 x2 plus 2 x3 equal to minus 20. Then solution, then A equal to, write the A matrix value is, then first equation x1 x2 coefficients, x1 x2 x3 coefficient. Then first equation x1 coefficient is 1, x2 coefficient is minus 3, x3 coefficient is 0. Then second row value is, then the second equation x1 coefficient is 0, x2 coefficient 1, then x3 coefficient 3, and the third row value is a third equation, then x1 coefficient 2, then x2 coefficient minus 10, x3 coefficient 2. This is a matrix, that is equal to, this matrix is a L into is converted to LU form, then the L value is 1 0 0 0 1 0 2 minus 4 1 into 1 minus 3 0 0 1 3 0 0 14, that is equal to L into U. Then first condition, first step, let Y equal to Ux, then solve the equation Ly equal to B. Then first write the L value 1 0 0 0 1 0 2 minus 4 1. Then Y values, then there's 3 by 3 order, then the 3 variables is given, 3 variables Y1 y2 y3 equal to, then B value is minus 5 minus 1 minus 20. Then write the three equations. Then first equation y1 y2 y3 are 0, then y1 equal to minus 5. Then second row y1 value 0, then y2 y3 value is 0, then y2 equal to minus 1. Then third equation, third row 2y1 plus minus 4y2 plus y3 equal to minus 20. Then substitute the values, y1 equal to minus 5, y2 equal to minus 1 in equation 3. Then the y3 value is minus 20 minus 2y1 plus 4y2. Then y1 y2 values are substituted, then minus 5 and minus 1. Then the final answer is minus 14. Then u3 value is minus 14. Then the second step, solve the following system ux equal to y. Then first write the u value 1 minus 3 0 0 1 3 0 0 14. Then the x, 3 variables x1 x2 x3, that is equal to minus 5 minus 1 minus 14. Then write the equations. Then first write the third row. Third row value is x1 value 0, x2 value 0, x3 is 14. Then 14 x3 equal to minus 14. Then 14 are cancelled. Their value is x3 equal to minus 1. Next write the second row value. Second row x1 value is 0, x2 value is 1. Then x2 plus 3 x3 equal to minus 1. Then substitute x3 value in equation 2, then x2 equal to minus 1 minus 3 x3, then that is equal to minus 1 minus 3 into x3 value is minus 1, that is answer is 2. Then for next write the first row equation, then 1x1 minus 3x2, then x3 value is 0 equal to minus 5. Then substitute the x2 value in equation 3, then x1 equal to minus 5 plus 3x2 equal to minus 5 plus 3 into x2 value is 2, then the answer is 1. Then the solution is then x1, x2, x3 value is then finding there, then the answer is x equal to x1 value is 1, x2 value is 2, then x3 value is minus 1. It is a solution.